Okay, so now we know how to measure vapor pressure. Then the next question is to be able to describe it. So when a liquid evaporates quickly, it means that the vapor pressure is high. So things like gasoline are very smelly. When we perceive smell, what we're actually kind of measuring with our noses is the number of gas particles. So I want you to tell me, does gasoline have a high vapor pressure or does it have a low vapor pressure? Okay, and that'll apply to nail polish remover as well, because that, of course, is pretty smelly. We can't smell solid things, or even liquids. The only thing we can smell is the gas particles that come off of them. So things that have a smell are producing gas particles that we can perceive. If something produces a lot of gas particles, then we call it a volatile liquid. Now, volatile also means flammable. So things like gasoline and acetone for nail polish remover are all flammable. Okay, so another way to think about vapor pressure is as a graph. So if I know the temperature, say I have some ethyl ether at exactly 20 degrees, I can figure out what the vapor pressure is at those conditions. So I'm going to use a ruler here to do this. Okay, so we go until we intersect with the line that we're interested in, and then we draw our line over here, and we find that ethyl ether, which is this molecule shown here, ethyl ether has a vapor pressure something around 410 torr at room temperature, which is about 20 degrees. Okay, so this tells me I can compare at 20 degrees. So here's ethanol, which again is, alcohol. And it's got a vapor pressure something like, 90 torr at room temperature. And water, I'm going to do water in blue, because why not? The line's blue, so water is way down here at 20 degrees. And its vapor pressure is super low. It's maybe 10 torr at room temperature. So what this tells me is the higher the pressure, so higher pressure, it means a higher vapor pressure, right? Okay, so that means more gas particles are there, which then if something is willing to go into the gas phase and not stay as a liquid, that means that it has very low intermolecular forces. So comparing water, ethyl alcohol, and ethyl ether, these three things, water has the strongest because it has the lowest vapor pressure here. Ethyl alcohol is the next one, and that means that ethyl ether is the weakest. All right, so we have kind of a continuum here. Okay. Now, so whenever we're, let me go to this one. Whenever we're changing state, going from, in that case it was from liquid to solid, it takes some energy to do that. Okay, so this is the boiling point we were talking about earlier, so BP, and it happens at 100 degrees, and you'll notice that that temperature for water is constant. Okay, so in other words, I'm putting in a bunch of heat because it's changing on the y-axis, right, but it's not changing the temperature. So then the question is, where does that energy go? Okay, and the answer to that question, where does the energy go, is basically it's going into the process we described where you're going from a condensed liquid into scattered atoms of gas. To do that, we have to break up the IMF. So the energy here is going into the process to break the intermolecular forces. And so the stronger the IMF, the higher the boiling point. Okay, so because they want to stay together, and in order to separate them, you have to put more energy in. All right, so that means the temperature that it boils is going to be higher. Ethanol would be on this graph if we were doing ethanol in, say, this red line. Ethanol boils at around 79, and then it becomes, gas form of ethanol. We like to abbreviate ethanol as ETOH because it's shorter. It would also, ethanol also has a lower a lower freezing point down here. So in other words, to get ethanol to freeze, you have to go all the way down to, I can't actually draw it on this picture because it would be like way down here, negative 114 Celsius. So by having weaker forces, weaker forces than water, ethanol boils at a lower temperature and it also freezes at a lower temperature. Okay. During these phase changes, we have names. For when boiling, we call it the heat of vaporization. That just means the amount of energy I have to put in to separate all of the intermolecular forces between the liquid and the gas. And then heat of fusion is the amount of heat needed to go from solid down here to a liquid up here. Okay. So on these diagrams, basically what's being represented is, let me just clean this up real quick. So what's basically being represented is you have solid material down here, liquid is next, and gas up here. And these flat regions are the phase change regions, either melting point, which is this one, or boiling point, which is this one. And the amount of energy needed to change the phase differs from one substance to the next, but in general, it's related to the underlying intermolecular forces. Okay, so the heat of fusion, this is actually not 355, this is 335 joules per gram, so you should fix that in your notes. The heat of fusion is how much energy is required to change 1 gram of something into a solid at the melting point. That's right. Into a solid at the melting point, which for water is 0 degrees Celsius. That means this is a conversion factor. So if I have 10 grams of ice, I just multiply by the number of joules to cancel the grams here. And we find out that it takes 3,350 joules of energy to melt the ice. On that diagram that we were just looking at, so I'm just going to sketch it up here. Okay, so this is solid, liquid, gas. On this diagram, that means that for 10 grams of ice, starting at 0 degrees, to get to become 10 grams of liquid water, which is still at 0 degrees, it takes 3,350 joules, which is quite a lot. That's quite a lot of joules. Okay, so we can use this strategy to calculate the phase change energy. And we can use a prior strategy that is familiar from 111, where if temperature is changing, we can use heat capacity, that's C, which is listed here, specific heat right there. We can use the mass and the change in the temperature of the material to figure out exactly how much heat is needed to go from, say, water at 0 degrees to water at 100 degrees. Okay, and so to do this, we did this in class together, but here's the math if you need to see this again. The most important step is after you have calculated, I would say actually the most important step is initially to sketch out what you're doing. So here we have our solid liquid gas thing again, okay? And this question says that we're starting with ice at 0 and we want to get it to 120 Celsius. So 100 degrees happens right here and 0 happens right here. And so if I'm starting with ice at 0 degrees, that means I'm starting right there. And I want to go all the way to 120, which means I'd be steam, right? So gas. So I got to find a Q for each one of these pieces. So we're going to have 4 total Qs. We're going to have the one when it's a liquid, one when it's a vapor, one where it's melting, and one where it's boiling. And I'm going to add all of those up, making sure that my units are the same. Okay, so those are the key tasks here. Now, so if each stage, so to melt it, to separate those intermolecular forces that hold something in solid phase, I have to add 39 kilojoules for water, for this particular sample. To go from the